All right, everyone. So in this video, we're going to go through the first part of lesson 1 of unit 2. So we're starting our new lesson, and we're going to be learning all about mole ratios. That's our new vocabulary word. And so is stoichiometry. So let's dive into it. So on the left, you see a recipe for a cookie. It's got 2 3/4 cup flour, a teaspoon of baking soda, half a teaspoon of baking powder, 1 cup sugar, 1.5 cups of white sugar, 1 egg, 1 teaspoon of vanilla extract. And all of this makes about 12 cookies. So what I want you to do is I want you to pause the video and answer the 3 questions off to the side. Press play when you're ready to talk about it. Okay, so now that you've kind of answered through those questions, let's take a look. So how many cookies could you make if you have lots of the ingredients, but you only have 2 teaspoons of baking soda? Well, for baking soda, since you need 1 teaspoon to make 2 cookies, or 12 cookies, that must mean that we can make 24 cookies. You can also set it up as a T-chart. If we have 2 teaspoons of baking soda, we know that 1 teaspoon makes 12 cookies, so that means we can make 24 cookies with our 2 teaspoons of baking soda. If we have 10 cups of flour and lots of everything else, how many cookies could we make? Well, if I have 10 cups of flour, what we know is that 2.75 cups of flour make 12 cookies. So in order to do this problem correctly, it would have to be 10 times 12 divided by 2.75, and that means we could make 43.6 cookies. So probably just 43 or 44 cookies, maybe 2 ones that are slightly smaller. And then number 3 says, okay, if I want to make 100 cookies, how many eggs do I need to buy? Well, if I have 100 cookies that I want to make, we know that 12 cookies require 1 egg. So that means 100 cookies divided by 12 means that you're going to need about 8.3 eggs. So you're probably going to want to go through several batches for that. So we can see here that in our recipe, we have our ingredients, right? These are the ingredients. And the cookies, that's the product. So in a chemical reaction, that would be like saying flour plus the butter plus everything else, right, produces the cookies. And this is similar, this relationship between all of the chemicals is what stoichiometry is all about. And yes, this is pronounced stoichiometry. And so stoichiometry uses the balanced coefficient, the balanced chemical equation of a reaction to discuss and use and study the relationships between the amount of your reactants that are used compared to the amount of product that is created. And so remember, when you have a chemical reaction, you always have your reactants and they produce your products. So the products are on the right side of the arrow, your reactants are on the left side. And so the way we can study these relationships is through their mole ratio. So what I want you to do is I want you to pause the video and read this paragraph, okay? While you're reading, I want you to underline or highlight or circle words that you think are key vocabulary words. Then press play when you're ready to review the answers to questions A through D. Okay, so as you're reading, hopefully you identified coefficient, mole ratio, reactant, and product as vocabulary words. Those words are repeated multiple times, but I only highlighted them once. So as you read, you should have recognized that the numbers that are in front of your chemical as our coefficient, that's where we get our mole ratio from. So for example, in the paragraph it said the mole ratio between hydrogen and water is 2 to 2. This part that I just highlighted, that's how you would say it out loud. And that comes from the coefficients that are in front of them. The mole ratio between oxygen and H2O is 1 to 2 because there's an invisible 1 in front of oxygen. Notice, since oxygen was listed first, the 1, which was the coefficient in front of oxygen, also went first. So when we look at these questions, it says, how many moles of sodium hydroxide are reacting? Well, your coefficient is your number of moles. So we have 6 moles of sodium hydroxide reacting because it is a reactant on the left side of the equation. And we know that 2 moles of the sodium arsenic are produced because there is a 2 as a coefficient in front of that. And then what is the mole ratio between arsenic and hydrogen? So since arsenic is listed first, we'll put the 2. And hydrogen is listed second, so we'll put the 3. If you were to put 3 to 2, that would be wrong, okay? Because arsenic is listed first. So D says, what is the mole ratio between sodium hydroxide and sodium arsenate? Well, we've got a 6, and then sodium arsenate has a 2, so we can say 6 to 2. You could also simplify that and say 3 to 1, but we normally just leave it exactly with whatever coefficients are in the equation. Okay, so let's look at how we can use mole ratios in a T-chart. So in Unit 1, we were learning how to use T-charts or dimensional analysis, okay? And we can use mole ratios the same way that we use molar mass and Avogadro's number. So remember before how we had these 2 equalities. We would say that 1 mole was equal to your molar mass in grams. And we said the same thing for Avogadro's number. And then that equality could be turned into a conversion factor where you had 1 mole on top and you had your molar mass in grams at the bottom, or you could flip the fraction. Well, we can do the same thing with molar mass, with mole ratio. So if the mole ratio of hydrogen to oxygen is 2 to 1, that's saying that you have 2 moles of hydrogen, because there's 2 moles of hydrogen in the equation, for every 1 mole of oxygen, since there's 1 mole of oxygen in the equation. And so that can be written as 2 moles of hydrogen over 1 mole of oxygen, or this version, which is just flipped, okay? And we can use that to make conversions, because the reason why is if I'm a company owner and I'm trying to produce this product, I need to know exactly how much of my reactants to buy. I don't want to waste any time or money, okay? And so what we have here is we have a problem that's been worked out for us. Okay, so here we see how many moles of H2O, so we've got what we're looking for here, moles of H2O, are produced by 27 moles of oxygen gas. So we've got 27 moles of O2 is what we are given. And so remember, we always analyze what we're given and what we're trying to find. And up until now, we've had 2 conversion factors that we could use. We had our molar mass measured in grams all over 1 mole, or, the flipped version. We also had Avogadro's number, 6.02 times 10 to the 23 particles, all over 1 mole, okay, or the flipped version. Or now we have the mole ratio. And so our mole ratio would be the number of moles of chemical A over the number of moles of chemical B, or flipped, okay? So in this case, the way you know that you need a mole ratio is when your chemical and your given and what you're trying to find is different. So notice here it says that because they were different, that's how we analyzed that we needed a mole ratio. Just seeing the unit moles here is not helpful because moles is in every single one of our equalities or conversion factors. So oxygen has a 1 in front, water has a 2. So that means the mole ratio can be written as 1 mole of oxygen over 2 moles of water. So let's say oxygen is blue, okay? Or it can be the flipped version, okay? So where the 2 moles of water is at the top or the bottom. So we can flip it. Now, when we start our t-chart, we always take what's given to us and we put it at the top. But since we have moles of oxygen at the top, that means that this has to repeat itself down here, which means that we will be using this conversion factor here because it's the only one that has moles of oxygen in the bottom. So then 27 times 2 divided by 1 gives us 54 moles of water because moles of oxygen are going to cancel out. So if you look, you can go ahead and answer these 3 problems or 3 questions based off of what we just reviewed, and you can start practicing with those.